Picture two things for me, side by side, and tell me honestly whether they could possibly look more different. On the left, a wave. Not a wave on any water, a wave of pure possibility, smeared out across the whole reach of space, humming quietly at every single point, and its one job is to whisper where some electron might turn up if you went looking for it. A cloud of maybe, spread everywhere at once. Now, on the right, a single atom, and one lonely little fact about it, the way it spins. No wave, no spread, no space to speak of at all, just a bare choice between two words, up or down. That is the entire thing, a smeared-out ghost on one side and a coin balanced on its edge on the other. And I am told that tonight you are going to look me in the eye and tell me those two are the same.
I am, and I know how that lands. Like telling you a thunderstorm and a light switch are secretly the same object. One of them fills the sky, the other clicks between two positions. Nothing whatsoever in common. But I don't mean they behave alike or feel alike, or that one is a dressed-up version of the other. I mean something far more outrageous. I mean they are the same kind of thing, cut from the same cloth, living in the same kind of place. And the moment you can see the place they both live in, every strange, spooky, sleep-robbing thing this month has thrown at you turns, quietly and almost embarrassingly, into geometry.
Geometry, as in shapes, arrows, the business with the triangles and the shadows from school.
That business. Arrows and shadows. That's very nearly the entire toolkit.
So let me get this straight before you take another step. We have spent a month now being told the quantum world is the deepest, weirdest, least knowable thing in all of science. Waves of possibility, arrows behind the odds, menus of allowed answers, uncertainty you cannot beat. And the grand reveal tonight, the thing you've apparently been holding back all this while, is a geometry class.
The spookiest theory anyone has ever written down. And underneath it, a room with some arrows in it. I'd feel a touch swindled too if I didn't happen to think it's one of the loveliest things a person can be shown. So let me earn it, line by line, and at the end, you tell me whether it was a con.
All right, earn it. Though I'll say this, I came in braced for mystery, and you have opened with the word shadow, so the bar is currently somewhere near the carpet.
The carpet's a fine place to start a climb. Here's the one idea the rest of the night grows straight out of, and it's almost insultingly simple, so don't brace, just take it. Whenever you've got a quantum system, any of them, the electron in its cloud, the atom with its spin, whatever you like, its state, meaning everything that is true about it right now, can be drawn as a single arrow.
One arrow. A single arrow for the whole state of the thing.
A single arrow pointing somewhere, in a space. And I have to be careful the instant I say space, because I do not mean the space you walk around in. I mean an abstract place, a made-up room if you like, where every possible state the system could be in is a different direction the arrow could point. Aim it one way, that's one state. Swing it round to point somewhere else, that's a different state. The direction the arrow points is the state. That's the founding move, that's the game.
Now wait, I want to be sure I'm not just nodding along to nonsense. This room, it isn't anywhere. I couldn't walk into it. It's not up on a little shelf somewhere inside the atom.
You couldn't walk into it, no, and it isn't tucked away on a shelf inside the atom. It's a bookkeeping space. A space of possibilities, not a space of places. Think of how you might chart a company by plotting its profit one way and its headcount another, and every possible company is a dot somewhere on the chart. That chart isn't a real room either, but it's a genuine space, and every point in it means something specific. Our room is like that, only what it charts is every way a quantum thing could possibly be.
All right, A space whose directions are possibilities, not places, and the state is simply which way the one arrow leans in it.
Which way the one arrow leans. And here is where the two pictures I opened with start falling into each other. That wave of possibility, the electron's cloud, that's an arrow in a space like this. The atom's spin, the bare up or down, that's an arrow too in a space like this. Same kind of object, the only difference between them is how roomy the room is.
How roomy? Meaning what? How big it is?
Meaning how many genuinely different directions the room lets you point in. Take the spinning atom first, because it's the humble one. How many truly distinct states did it have at bottom? There was up, there was down, and then every mixture of the two. But a mixture is just the arrow swinging round between up and down. It isn't a new wall. So the room for a spin is tiny. A couple of directions to build everything out of, and the arrow lives in the little space those two open up. A cramped room, almost a toy.
A couple of directions, that really is small. And the wave? The electron smeared over all of space?
Ah, now the room gets frightening. Because the electron could be found here, or there, or a hair to the left, or a hair to the right, or anywhere at all. And every last one of those could be right here possibilities is its own separate direction in the room. A distinct way for the arrow to lean. And there are as many of those directions as there are points in space to be found at. Which is to say, a staggering number, well past counting. So the wave lives in a room with a dizzying forest of directions, and its one arrow leans a little toward every one of them at once. A little toward here, a little toward there, a little everywhere.
And that, leaning a little toward everywhere at once,
that is the smear. That is the cloud. The thing you were picturing as a fog spread over space is really one arrow in an enormous room tipped gently toward a huge crowd of directions. When you flatten that arrow back down and ask, so where's the fog thickest? You get the smear you started with. But the smear was only ever the shadow of it. The real thing was the arrow.
So the smeared-out wave isn't smeared at all. It's a single arrow in a gigantic room, leaning toward an enormous number of directions.
A single arrow in a gigantic room. That's it exactly. And the coin, the spin, is the same animal, the same arrow, just photographed in a room with barely any directions in it at all. The wave and the coin were never two species of thing. They're one creature, met once in a vast room and once in a cupboard.
I need to sit with that a moment. A month of being told the wave function is this profound, ineffable object, and the punchline is it's the same as a coin flip, only in a bigger cupboard.
In a considerably bigger cupboard. But, yes, though I'd push back gently on only, because the size of that cupboard is going to come back at the very end of the night and try to swallow us whole. Keep it in your pocket. For now, just hold the founding move. A state is an arrow, and it lives in a space of every state the system could be in. We even have a plain name for the room. We'll call it the space of all states.
The space of all states. Not named after anybody, I notice. Everything else in physics is named after some fellow with a beard.
There's a name for it in the textbooks, welded to a person, and it does the idea no favours whatsoever. So tonight, the beard stays at the door. The space of all states. Say what the room is, not whose it is. And the rule of the room is simple. Every direction you could point that arrow is a state the system is allowed to be in.
And every system gets its own room. My electron, your atom, some whole molecule, each with a different space.
Each with its own room, sized to its own possibilities. But always the same kind of room, playing by the same short list of rules. That's the quiet promise of the whole night. One blueprint, stamped out at every size you like. The electron's room is vast. The spin's room is a cupboard. A molecule's room is vaster still. But learn the moves in the toy room, the little up and down, and you have genuinely learned them everywhere. Adding arrows means the same thing in the cupboard as it does in the cathedral. The room changes size from one system to the next. The rules themselves never so much as flinch. That's the one thing that lets a single evening cover a whole month.
Fine, I've got the room, and I've got the one arrow leaning in it. Now, you promised the weird stuff turns into geometry. Start turning it. Give me the first spooky word and geometry it in front of me.
Gladly. Let's take the most mystified word in the whole subject. Superposition. The word that has sold 1,000 paperbacks with quantum on the cover. A particle being here and there at the same time. Up and down at once. Alive and, well, you know the poor cat.
The cat. Everyone always drags in the cat. Here and there, up and down, the thing that supposedly melts your brain. Go on then, geometry it.
You take 2 arrows and you add them. That's the whole thing.
That is not the whole thing. You cannot smuggle the deepest idea in the subject past me in 6 words.
I can though, and I just did. So watch me do it slowly, to be fair about it. You've got an arrow that means here. You've got a second arrow that means there. Lay the second one's tail right at the first one's tip. Nose to tail, the way you'd add up 2 steps across a room. 1 step and then the next. And draw a brand new arrow from the very start to the very finish. That new arrow points somewhere new. It's a new direction. So it's a new state. And that state is here plus there. Both at once. That's superposition. It's arrow addition. It's the very thing you already do when you walk 2 blocks east, then 1 block north, and work out where you ended up.
So up and down at the same time is
The up arrow added nose to tail to the down arrow, giving you a fresh arrow pointing off between them, which is a perfectly good direction in the room. So it's a perfectly good state. And that's the deep rule of the space of all states, the only one that truly matters. Add any 2 allowed arrows, and you always land on another allowed arrow. Add 2 states, get a state. The room is built so you can never, ever fall out of it just by adding.
Hold on though, that feels almost too easy, and I've learned to distrust you when it's easy. If I can add any 2 states and always get a legal state, then the legal states aren't some rare, special little list. They're everywhere. Every direction counts.
Now you're seeing it. Every direction in the room is a legitimate state. And that's exactly why superposition isn't some rare, exotic condition the particle occasionally slips into on a bad day. It's the ordinary case. A state pointing cleanly along up, dead straight along one wall. That's the unusual one, the tidy special case. Point the arrow anywhere else, anywhere in between, and you've got a superposition automatically, for free, just by not lining up with a wall.
So all that breathless talk, the particle is in 2 places at once, really just means the arrow isn't lined up with a wall.
The arrow is pointing at an angle. That's the whole confession. Superposition, the great mystery, deflates all the way down to the arrow's leaning somewhere in between. And I want to be honest that this genuinely is a deflation. The air is meant to hiss out of it. Because the mystery was never really in the adding. We only ever needed a picture in which adding 2 states was allowed to mean something plain. Now we've got the room, and adding arrows means combining states, and here plus there stops being a paradox and becomes arithmetic.
But hang on, if I add 2 arrows nose to tail, don't I sometimes land on a longer arrow or a shorter one? You told me every state is supposed to be the same length.
Sharp of you. And yes, you do. Add 2 arrows and the sum can come out the wrong size entirely. So we do one small, tidy step afterward. We gently stretch or shrink it back to the standard length, back onto that ball around the center of the room, without ever touching the direction it points. Because the direction is the state, the length is only bookkeeping we like to keep neat. Two arrows that point the very same way but come out different lengths are the same state, said loudly and said softly. Superposition is only ever about which way the sum points, never about how long it happened to come out of the adding.
Let me hand you a concrete one to be sure it isn't just pretty words. Last week's atom, the one that was definitely spin up.
The perfect test. A definitely up atom, you'd think, is the simplest, least mysterious thing there is. It's just up, surely, nothing added, no superposition anywhere in sight. And yet the moment you asked it a sideways question, left or right, it came apart into half and half, remember? That's because up, drawn as an arrow, is itself the left arrow added to the right arrow. Certain up is already a superposition of left and right, sitting there in plain view, and you'd never have known until you thought to ask the sideways question. The mixture was baked in. It was only ever a matter of which wall you held it up against.
So the atom that was most smugly certain about itself was quietly two things at once the entire time, and simply never mentioned it.
Never breathed a word. Because from its own point of view, there was nothing to mention. It was one arrow, pointing one way. Superposition isn't something the atom is busy doing. It's something we notice when the way the arrow happens to point doesn't line up with the question we walked in carrying. Which is the perfect moment to bring in the thing that asks the question. We've got the arrow, the state. Now we need the second character, the thing that does the asking.
The observable, the thing you actually measure, position, energy, spin, whichever.
Any of them. And a few weeks back, we learned to think of each of those not as a number sitting on the particle, but as an action you perform on the state, an operation. Tonight that operation finally gets a shape you can see. Because here is what an observable really is, inside the room. Each one lays down a set of axes across the space. A frame. It's as if you walked in and nailed a fresh set of reference directions to the walls. This way is one axis, that way another, set at their angles to each other. Every question you can put to the system comes carrying its own frame of axes to hang up in the space of all states.
Axes, like the ones you plot a graph against, the lines you measure distances along.
Exactly those. And two things get pinned to each frame, and this is the part to really hold on to. First, the directions of the axes themselves. Those are the special, settled states of that observable, the states where the question already has one definite, sit-still answer. No mixing, no maybe. The states that a measurement leaves completely alone from a couple of weeks ago. They are the axis directions of the frame.
So the settled states, the ones a measurement doesn't disturb, those are literally which way the axes point.
Literally which way the axes point. And the second thing pinned to the frame, written along each axis like a number chalked on a ruler, is the answer you get if the arrow happens to be lying flat along that axis. The label. So an axis is a settled state, and the number chalked along it is the value that goes with that state. State and answer, welded together into one direction.
The axis is the state, the label is its answer. And how many axes does a frame get?
As many as the question has possible answers, no more, no fewer. Which is the whole reason the answers come in a fixed list at all. Cast your mind back to the menu a couple of weeks ago. How a measurement can only ever hand you one entry off a fixed set of results, never anything in between them. There's your menu, sitting right there in the geometry. The answers a question can return are just the labels chalked along its axes.
So the menu is the set of labels on the walls.
The menu is the set of labels. That's why an atom's energy comes on a fixed ladder, rung by rung, and not on a smooth ramp. Because energy's frame has a fixed set of axes, and each rung of the ladder is a label chalked on one of them. There's no rung between the rungs because there's no axis between the axes. The gaps in the menu are just the gaps between the walls.
And these settled states, the axis directions themselves, a measurement really does leave them completely alone.
Completely alone. That is exactly what makes them settled. If the arrow is already lying flat along an energy axis, you ask the system its energy and it just hands you that rung calmly and doesn't so much as twitch. No snap, no drama, no dice rolled at all. It was already home. The question found it exactly where it lived. The whole commotion of measurement, the roll, the snap, only ever breaks out when the arrow is tilted away from the axes you're asking about, when it has to be dragged flat onto one of them against its lean. Line your question up with where the arrow already lies, and measurement turns into the gentlest thing in the world.
So the universe really is a restaurant with no substitutions, and the menu is chalked on the walls.
Chalked right along the axes. And now here comes the move that unlocks the rest of the night. Ask a different question. Measure a different observable, and you hang up a different frame, a different set of axes, and in general, they're turned at some angle to the first set. Same room, same one arrow sitting in it, unchanged, but a whole new set of walls to measure it against.
Give me that in the concrete again, the spinning atom. Where were its frames?
The toy room, ideal for this. Asking, is the spin up or down? Hangs up one frame. Two axes, one chalked up, one chalked down. Now ask instead, is the spin pointing left or right? That's a second frame. Same little room. But its two axes, left and right, are just the first frame's axes turned partway round. The very same space, with the axes rotated to a new angle. Two questions, two frames, tilted against each other.
Here's what still nags me though. In the ordinary world, when I measure something, the length of a table, say, I'm only reading off a number that was already sitting there. Is a quantum measurement really so different from that?
It is the whole difference between the two worlds, and you've put your finger right on the seam. Measuring the table reads a number that was already there, resting on the wood, waiting patiently for you to notice it. But a tilted quantum arrow has no single number sitting on it. It has shadows, several of them, leaning several ways at once. So the measurement isn't reading a waiting answer off the arrow. It's forcing one answer into being, and then snapping the arrow flat to match the answer it forced. In the everyday world, you find out what was already true. In the quantum world, the asking helps to make it true. Same tired old word, measure. Two completely different acts underneath.
And you keep telling me to hold on to that tilt.
Hold it like it's hot, because that tilt is about to turn out to be the whole reason those two questions couldn't be answered at once last week. But not yet. First, let me pay off the thing you asked for ages ago and I keep dodging. You go and look. The world hands you one wall. How? How does an arrow leaning off at some angle ever cough up a single, definite answer?
Yes, that. The arrow's leaning off between the axes. I go to measure. What does the geometry actually do?
It casts a shadow. That's the whole of measurement, and it's my favorite sentence in all of physics. To measure an observable, you take your state arrow and you throw its shadow onto that observable's axis. You project it. Shine a light square across the frame and see how far the arrow's shadow reaches along each axis. That reach, the length of the shadow the arrow throws along a given axis, is how strongly the state leans toward that particular answer.
So an arrow pointing off between up and down throws a shadow onto the up axis and a shadow onto the down axis.
A shadow onto each. And if the arrow leans mostly toward up, its shadow along the up axis is long, and its shadow along the down axis is short and stubby. Now, A question for you. What did we call that shadow length a couple of weeks ago, before we had any of this machinery? Back when we first drew the little arrows behind the odds.
The amplitude, the length of the little arrow, the thing you square to get the probability.
The amplitude. The shadow the state arrow throws along an axis is that. The amplitude for that answer. And then you do the one and only thing we ever learned to do with an amplitude. You square it. Take the length of the shadow, square it, and out comes the probability of getting that answer. That's the odds rule, the one from 2 weeks back. And here it stops being a decree handed down from a mountain. It's just the shadow squared. Long shadow, big square, likely answer. Short shadow, tiny square, unlikely answer.
So the mysterious probability rule, the one that felt carved in stone and handed down, is measure the length of a shadow and square it.
Measure a shadow and square it. That's the entire thing. And watch the toy atom do it. The certain up arrow, thrown against the tilted left-right frame, casts a shadow of equal length onto left and onto right. Square each, equal squares, and there's your half and half. The coin toss you saw last week wasn't the atom being wishy-washy. It was one arrow throwing two shadows of the same length, and the squaring turning those two shadows into even odds.
And there's no hidden fact about which way it really was.
None to be had. The arrow was pointing up. That's the whole truth about it. Left or right simply wasn't a question the arrow had a flat answer to. It had two shadows instead of one, and shadows are all the world gives you. But here's a small piece of grace buried in the squaring, which I can't resist showing you, because it's the reason the whole thing holds together. We keep every state arrow the same length. Picture all the legal arrows reaching out to just touch one ball around the center of the room, every one the same size. Now drop that fixed length arrow's shadows onto a full set of axes and square each one. Those squares add back up to exactly the arrow itself, to 1.
The squares of the shadows add up to the whole arrow. That's the triangle rule from school. The square of the long side is the sum of the squares of the others.
The very same rule you met with triangles, grown up a little and moved into a bigger room. And what it means here is quietly magnificent. The odds of all the possible answers always total 1. Automatically, for nothing, because the arrow had a fixed length to begin with, and its shadows have to account for all of it. There's simply nowhere else for the arrow to hide. The probabilities can't help but add up right.
That's genuinely lovely. The odds add up to 1, not because some rule was bolted on afterward to force them to, but because the arrow was always the same size, and its shadows have to add up to the whole of it.
They have to add up to the whole of it. There is nowhere else for the arrow to go. But I've only done half of measurement so far. The shadow gives you the odds of each answer. It doesn't yet tell you what happens to the arrow itself the instant you actually look. And that part, that's the rude part.
The rude part. I've been waiting all night for the rude part.
The instant you measure, the instant the world commits to one answer, the arrow snaps. It stops pointing off at its clever in-between angle, and it swings, hard, right onto the axis of whatever answer came up. You measure and get up, then bang, the arrow is now lying flat along the up axis, not leaning toward it, lying on it. Flat. The superposition is gone. Whatever else that arrow used to be tilted toward is simply wiped away.
That's the snap, the collapse, the thing from a couple of weeks ago where the very act of asking changes the thing you asked about.
That's the snap, and now it's a picture you can actually watch happen. Before you look, an arrow tilted somewhere out in the room, leaning toward several answers at once. You look. The world reads off the shadows. The squared shadows set the odds. One answer wins the roll of the dice, and the arrow flops flat onto that answer's axis and just stays there, frozen against the wall. And here is the quiet thing I most want you to notice about what we've done.
Go on.
Amplitude, odds, and collapse. For weeks, those were 3 separate rules you had to swallow one at a time. The little arrow behind the odds, the squaring that turns it into a probability, the snap when you look. 3 commandments memorized cold. And they have just become one motion. Cast a shadow, square it, snap onto the axis. One geometric gesture done in a single breath. There aren't 3 rules anymore. There's an arrow and its shadow and where it lands.
I have to say, I love that the deepest, most agonized over act in all of quantum mechanics, the measurement, the collapse, the thing that broke 100 careful physicists, is, in your telling, taking a photograph of an arrow's shadow and then rudely insisting the arrow was lying flat against that wall the whole time.
That's the crime, near enough. You photograph the shadow, you announce the verdict to the room, and then you shove the arrow flat against whichever wall you just named, and it lies there looking for all the world as though it had never once pointed anywhere else in its life. Measurement doesn't merely read the state, it rearranges it. But, and this matters enormously, it rearranges it in a completely lawful way. It snaps to an axis, always an axis, never to some random spot on the floor. The rudeness has rules.
All right, I'll concede. That's 4 separate mysteries you've folded into one drawing now. The state, superposition, the menu, the whole business of measurement. That's more than I bargained for, and I resent how tidy it's getting. But you keep dangling that tilt in front of me. The 2 frames turned against each other. You said it was the entire reason 2 questions can't be answered at once. I want it. Now.
Then here's the deepest thing of the night, and I'm going to go slowly, because when it lands it ought to feel like a floor giving way. In the good direction. Remember the 2 frames for the spinning atom. Up and down, 1 pair of axes. Left and right, another pair, the same axes turned partway round. Tilted against each other. Now, suppose I get my atom into a state with a perfectly definite up-down answer. Knife sharp. Certainly up. No doubt in it anywhere. Where's the arrow?
Lying flat along the up axis, dead straight along it. No tilt, no mixing. It's simply up.
Lying dead flat along up. Beautiful. Now I put the other question to it. Left or right? And to answer that, what do I have to do?
You throw its shadow onto the left-right frame, the other set of axes.
I throw its shadow onto the left and right axes, but those axes are tilted. So this arrow, which is lying perfectly flat along up, sharp and certain and rather pleased with itself, cannot possibly lie flat along the left axis or the right axis, because both of them are turned at an angle to it. It has no choice in the matter. It must throw a shadow onto both of them. A shadow onto left and a shadow onto right. Both real, both there. Neither one of them zero.
And a shadow on both axes means
It has no definite left or right answer at all. It leans partly toward left and partly toward right. In this case evenly, half and half. Ask it and you get a coin toss. The arrow that was so perfectly, knife-sharply certain about up is forced, by nothing whatsoever except the tilt of the 2 frames, to be completely undecided about left and right. It could not be sharp on both at once. The geometry simply forbids it.
because you cannot lie flat along an axis of 2 tilted frames at the same time.
You cannot lie flat along an axis of 2 tilted frames at once. That one sentence is the uncertainty principle. The whole of it. The very thing we spent an entire week on and called the blur you cannot beat. It was never about clumsy instruments or jostling the particle when you go to poke it. It's this, and only this. A state that lies cleanly along one question's axis must spill its shadow across the other question's axis whenever those two frames are tilted. Sharpness here buys you blur there. Not because you're clumsy, because the arrow is one arrow, it can only lie flat in one direction, and the two rulers don't even agree on which way flat is.
And if the two frames did line up, if they weren't tilted at all,
then there'd be no uncertainty between those two questions at all. And that's the honest other half of it. If two frames share their axes, an arrow lying flat along one is lying flat along the other in the same breath. Sharp here, sharp there, both at once, no trouble. Those are the questions you can answer together, the compatible ones. Uncertainty only shows up between questions whose frames disagree. No tilt, no blur. All the tilt in the world, all the blur in the world. It's a dial, and the tilt is the dial.
give me something I can actually see on a kitchen table. This tilt, these shadows. Make them real for a second.
Hold a pencil straight up and shine a light down from directly overhead. And look at its shadow on the table. A tiny dot. All the pencil's length is standing up. None of it is lying along the table, so the shadow is next to nothing. Now slowly tip the pencil over. The shadow stretches out longer and longer across the table, while the standing up height shrinks away. And here's the whole thing. You cannot have both at once. A long table shadow and a tall standing height. Impossible, because it is one pencil, with only so much length in it to share out between standing up and lying down. Sharp one way costs you the other every single time. That trade, that exact trade, is your uncertainty. One arrow made to share its single length between two axes that flatly refuse to line up.
So the whole of uncertainty, the thing that felt like the universe deliberately hiding something from us, is really just two frames that refuse to line up. Two carpenters who cannot agree which way is up, both trying to measure the same arrow.
Two carpenters who can't agree which way is up. That's it, precisely. And last week you watched exactly this play out on a bench, though you didn't yet have the picture for it. 3 magnets in a row. You measured up-down and got a sure up. Then you measured left-right and it scattered half and half. Then you measured up-down again, and the up you'd been so certain of was gone, back to half and half. Everybody finds that maddening.
I certainly did. I'd already filed the answer, and the universe shredded it while my back was turned.
But look at it now, with the room in front of you. Asking the tilted question snapped the arrow flat onto a left-right axis, which is tilted away from up. So of course, when you came back and asked up-down again, the arrow had to spill its shadow both ways once more. Nothing was jostled, nothing was clumsy. The arrow simply can't lie flat in two tilted frames at the same time, and every time you measured, you snapped it flat into a new one.
And there's genuinely no cleverness that buys you out of it. No finer instrument, no gentler touch.
No finer instrument, because it was never the instrument. It's the arrow being one arrow, in a room where two frames disagree about straight. You could build your measuring device out of moonlight, and it would not help you one bit, because there is nothing broken to fix. The world isn't being coy with us, it's being geometrical. And if you want the most vicious pair of tilted frames there is, the two turned hardest against each other of all, its position and momentum. Where a thing is, and how it's moving.
The two you can never pin down together.
Those two. Their frames are tilted so hard against each other that an arrow lying dead flat along a single position, one exact spot pinned to a point, has to throw its shadow evenly across every last momentum axis at once. Utterly sharp in place, utterly smeared in motion. Nail down the where, and the how fast simply explodes across all of its answers. That's the blur you couldn't beat. drawn as pure geometry. It's the tilt, taken all the way to its limit.
All right, you've well and truly earned the tilt. Now, you keep saying stand back. I think it's time. Stand me all the way back and let me see the whole thing at once.
Then here it is. The thing I've been waiting all month to be allowed to say. Look at everything we struggled with, week after week, one strange creature at a time, and watch it collapse into a single picture. The quantum state, the wave, the spin, all of it is an arrow in a space of all its possible states. Superposition, here and there, up and down, the mystery of mysteries, is adding two arrows and getting a third. An observable, position, energy, spin, any question you can put to the world, is a set of axes laid across that space. The allowed answers, the menu, the fixed ladder of an atom's energies, are the labels chalked along those axes. Measurement is a shadow, squared, and then a snap onto the axis you land on. And uncertainty, the deepest of the lot, is nothing but two of those frames tilted against each other.
Say it once more, slowly, because I think what you're telling me is that they were never separate things at all.
They were never separate things. That's the whole of it. The wave of possibility we met first, an arrow in a vast room. The little clock hands behind the odds. Those are the shadows the arrow throws. The menus, the operators, the entire apparatus of measurement. That's axes and labels and shadows. The spinning atom, the two spots on the screen, the qubit, the same arrow in the smallest room there is. Every single thing that made your head ache this month was one geometry, glimpsed through a different doorway. We kept walking into the same room through different doors and swearing each time we'd found a different room.
And it's all one space? Not a separate room for each, a room for waves, a room for spins?
For any one system, one room. One space of all its states, and every question you can ask is just another frame of axes hung up inside that same room. You don't change rooms to change the question. You change which walls you measure against. That's the unification, not that the mysteries resemble one another, but that they're the same handful of moves, performed over and over in one space, on one arrow.
So the whole month really was one single lesson, just taught in 5 different disguises.
One lesson in 5 disguises, and I genuinely couldn't have told you that on the first night. If I'd opened the month with, "Relax, it's all just arrows in a room," it would have landed as nothing. Empty words, a slogan on a mug. You had to feel the wave be strange in its own right, and the odds be strange, and the menu and the spinning coin and the blur you couldn't beat. Each of them had to unsettle you on its own terms first. Only then could the single shape underneath them all land with any weight at all. A unification is worth exactly as much as the pieces it cost you to earn it. That's the honest reason it had to wait all the way for tonight.
So when somebody says the words, the quantum state, the thing this entire subject is supposedly about, what they are really pointing at is
an arrow in the space of all states. That's it. That's what the quantum state is. Not a wave, not a cloud, not a coin, not a list of odds. Those are all just what the one arrow looks like when it throws its shadow onto one wall or another. Underneath every last costume, an arrow in a room. That is the thing the whole subject has been circling since the first night. One shape.
I came in braced for the deepest mystery in all of science, and you've handed me an arrow in a cupboard. I honestly cannot decide whether to feel enlightened or robbed.
Both. Feel both at once. You're allowed. You've earned a little superposition of your own. That double feeling is the correct response to good physics. The world was hiding something enormous, and the enormous thing turned out to be simple, and simple is somehow the bigger shock of the two. Nobody ever promised the secret would be complicated. It only ever had to be true.
All right, but you're an honest sort, and I can feel a but building somewhere behind your teeth. We've kept this to arrows and shadows all night long. Where have we been fibbing? Where is the picture a little too clean to be the whole truth?
Fairly asked, and I'd far rather you knew the edges than believed I'd shown you the whole beast tamed. Nothing we've said tonight is a lie, but the real thing is written in a precise mathematics of these arrows and exactly how their shadows fall across one another, and we've deliberately kept it as arrows and shadows with no symbols on the table between us. There are two edges worth naming out loud, so you know where the drawing stops.
Name the first.
The room can be bigger than any room. For the little spin, a couple of directions. For a wave spread over space, a forest of them past counting. And the space of all states can have endlessly many directions, more than any room you could ever build or picture in your head. We've drawn it tonight as a cozy little space with a handful of walls, because a handful of walls is what a person can actually see. But some of these spaces have no end to their walls at all. The drawing is honest about the shape, it just cannot be honest about the size.
And the second edge?
The second is subtler, and it's a small debt I owe to a couple of weeks ago. All night I've said shadow length, as though the shadow were only a length, a plain, honest number. It isn't quite. Each shadow is itself one of those little turning clock hands from the arrows behind the odds. It carries a length and a little direction of its own, a tiny hand pointing somewhere round a dial. And that's not a decoration. It's the whole reason states can interfere. The reason two shadows can line up and add to something brighter, or turn against each other and cancel down to nothing at all. The arrows carry that little turning clock inside them everywhere they go.
So the real thing is richer than a chalk drawing on a flat board.
Richer, yes. But, and this is the part that matters, none of it knocks down a single beam of what we drew. The skeleton holds. It's still a state that's an arrow, an observable that's a frame of axes, a measurement that's a shadow squared and a snap, an uncertainty that's tilted frames. The turning clock hands and the endless directions are extra rooms built onto the house. They don't move the foundations by so much as an inch. The geometry is the honest picture. We haven't cheated to draw it. We've only drawn it small enough to fit inside one evening.
Then let me push my luck, because you told me right at the start to keep the size of the cupboard in my pocket, and I've been carrying it around all night, waiting. You made a great deal early on of how the wave's room had a terrifying number of directions. That wasn't just colour, was it? That was a fuse you were lighting.
It was a fuse, and you've picked it up by exactly the right end. So let me light it properly. One particle needs a room with a certain number of directions. Small, manageable. You could keep track of that arrow on the back of an envelope over lunch. Now bring in a second particle. You might reasonably guess the room just doubles up, adds another envelope's worth of directions. It does not. The directions multiply. Every state the first particle could be in, paired with every state the second one could be in. The number of directions blows up by multiplying, not adding.
Multiply, not add. So it doesn't grow, it detonates.
It detonates. Add a third particle, it multiplies again. A fourth, again. Every single particle you toss into the room doesn't lengthen the list of directions. It doubles it, and then doubles the doubling. And doubling doesn't crawl along politely. It sprints clean off the edge of the world. A handful of particles, just a handful, mind you, and the number of directions in that room races straight past every computer we have ever built, or ever could build.
Wait, you're telling me that to honestly write down what a mere handful of particles are doing, arrow and all, you would need more room than there is stuff in the entire universe to write it in.
A little more than a handful, and the number of directions sails clean past the number of atoms in all the stars in the sky. To hold the full arrow for even a modest little clump of matter, we'd need a machine bigger than everything there is. It cannot be done. Not with a faster computer, not with a cleverer one. Not ever, Not that way.
And yet,
And yet. Here's the thing that ought to keep you awake tonight. That handful of particles, that ordinary speck of matter sitting on the table, minding its own business, is doing it. Right now. Effortlessly. Every atom in your hand is tracking its own monstrous arrow in its own unthinkably vast room, every instant, without strain, without a computer, without so much as appearing to try. Nature keeps every last one of those numbers, everywhere, all the time, and it never once sends a bill.
that genuinely stops me cold. The speck of dust is outcomputing every machine we will ever own, and it isn't even paying attention.
Not even glancing at the problem, and finishing it flawlessly, every instant, in every last corner of itself. There is a real vertigo in that, if you let yourself stand at the edge of it. The universe isn't tucking these monstrous arrows away in some cosmic filing cabinet and grinding through the arithmetic overnight. It simply is the arrows. For nature, being a quantum thing and keeping perfect track of a quantum thing are not two jobs, they are one and the same act. The impossible sum comes out free because, for the universe, existing and computing are the very same motion. We are the only ones who have to do it the hard way, with a pencil, from the outside, looking in.
So, nature runs the impossible sum without breaking a sweat, and the moment we try to follow along on paper, we go straight under.
We drown at the second particle, and it only gets worse from there. Which leaves us holding a question that sounds, at first, like flat despair, but is, I promise you, the single most exciting question this whole course has been quietly walking toward from the very first night. If the room is too big for any machine we could ever build, then how on earth could we ever compute what nature is doing inside it? How do you keep pace with something that outcomputes the entire universe just by sitting perfectly still?
And I take it you are not going to answer that one for me tonight.
Not tonight. Because the answer is the payoff of everything. Every week, every arrow, every shadow we've drawn, and it has earned its own evening. But I'll leave you the shape of it, the smallest glint of it, to carry out the door. If an ordinary machine chokes on nature because it's built of ordinary parts, then perhaps you shouldn't be fighting nature with the wrong stuff at all.
Meaning, build the machine out of something else entirely.
Build it out of the very same thing nature is made of, out of these little rooms themselves, out of the qubits from last week, real things that live in a space of states of their own, that superpose, that cast shadows, that carry those turning clock hands. A machine like that wouldn't have to laboriously store nature's impossible pile of numbers. It would simply be a quantum thing that already has them. You'd let quantum keep pace with quantum. That, believe it or not, is where this entire course has been headed all along. But that, truly, is a story for next time.
A machine built out of the very thing you're trying to study. I have to say that sounds suspiciously like cheating.
It sounds like cheating, right up until you notice that nature has been doing exactly this the entire time, and simply calling it existing. All we're proposing is to borrow her trick, at a size we can hold in our hands. Build a small, tame, steerable quantum thing of our own. Let it live in the same kind of vast room, with the same arrows and shadows and turning clocks, and then let its arrows act out the rules of the wild, quantum thing we could never compute. It isn't a drawing of nature, and it isn't a metaphor for nature. It is a piece of the same stuff, put to work, standing in for the piece we actually care about. But, next time. I truly mean it this once.
Then leave me with just the one thing to carry home. After a whole month of separate strangenesses, the wave, the odds, the menu, the two spots, the uncertainty, what is the single thing I now know, walking out of here, that I didn't know walking in?
That they were never separate. That underneath the wave of possibility, and the arrows behind the odds, and the menu of allowed answers, and the bare little coin of spin, and even the blur you could not beat. Under every last one of them, there was one shape all along. An arrow, in a space of everything it could be, throwing its shadow onto whatever question you happened to think to ask. That is the quantum state. That is what all the strangeness was, the entire time. Geometry, wearing a great many frightening masks.
One arrow, one room, and a month of ghosts turning out to be the same shape, just seen through different doors. You know, I think that's the closest thing to a magic trick anyone has ever shown me that got more wonderful the moment I was told how it was done. So, next time then, how you build a machine out of the very stuff nature is made of, and set it loose to chase nature down its own impossible corridors. But for tonight, this is plenty, more than plenty. The whole quantum world was hiding one clean shape, and now, at last, we've seen it. That'll do. That will more than do.